Now that we can understand and simulate the behavior of a true second-order system when we give it a step function as an input, we can see what happens when we modify our true second-order system to have an extra pole and be a third-order system, or when we have a 0 in the numerator, and we can see how this is going to modify the behavior of our system. As a quick refresher, let's look back at our first-order systems from last lecture. And remember, in our basic first-order system we analyzed, we had degree 0 numerator, degree 1 denominator, and we knew what the behavior was going to look like. But then we saw that if we added a 0 in the numerator, that the behavior was going to change. Now, in the first-order system, we saw that that caused a non-zero starting point at time equals 0. We're going to see different behavior in our second-order systems, but the idea here is if we can modify it from its baseline behavior and still be able to make some sort of analysis. So what happens in our second-order system when we add zeros or we add poles to it? All right, so first let's look at some general things that are going to happen in our system, in our second-order system. So if we add an extra pole, making it a third-order system, it depends where that pole is located. So if we have a pole in the left half plane, in addition to our 2 poles from our underdamped system, a third pole in the left half plane is going to increase the rising time and decrease the overshoot. And if we increase the rising time, we're also going to be increasing the peak time. But increases the rise time, decreases the overshoot, and it does it significantly if that third pole is within 4 times the real part of our dominant poles. And we'll see in our example in a little bit how we calculate that. But if it's what we call close to our dominant poles, it's going to have a significant effect of increasing the rise time, peak time, decreasing the overshoot. And if that third pole is in the right half plane, so it has a positive real part, or it's a positive real number, it's going to make the system unstable. And again, we already know this from when we looked at initial value theorem, final value theorem, that a condition on applying those is that all the poles were in the left half plane. And we know that a pole in the right half plane will make it unstable. And in general, when we add a 0 to our system, so we have a 0 in the numerator instead of no 0 in the numerator, in general, a 0 in our left half plane, so the real part or the real 0 being negative, is going to be increasing our overshoot, decreasing our rise time and peak time, and is going to be significantly affecting it if it's within 4 times the real part of the dominant poles. So a 0 in the left half plane has the opposite effect as a pole in the left half plane, decreasing our rise time and our peak time and increasing our max overshoot. Now, we can put a 0 in the right half plane without the system becoming unstable, but we're going to see that it has kind of odd effects on the system's response. So generally, poles and zeros, if we're adding them, we want them to be in the left half plane. I'll talk in a minute about how do we actually add these things, or why would we have extra zeros and poles in our system. And then finally, we could have an extra pole and an extra 0 in our system instead of just one or the other. So the general rule is if they're close to each other, they may cancel each other out. Again, we can see a left half plane 0 has the opposite effect as a left half plane pole. So when they are close in value, then pretty much the net effect is no change to our baseline system. All right, so again, to summarize it, left half plane pole decreases overshoot, increases rising time and peak time, and especially we'll see this happen significantly if it's within 4 times the dominant pole. So how we're going to add them or kind of consider them is we're going to be comparing our baseline system, and then what if we have an extra pole in the denominator, and we'll add it in this form of an s over negative p plus 1. And again, in short, a 0 in the left half plane is going to have the opposite effect. Increases our overshoot, decreases rise and peak time, and significantly so if it's within 4 times the real part of our dominant pole. And we'll add zeros in the form of s over negative z, where z is the 0, plus 1. Right? So we'll see how this affects our systems in a moment. So I keep using the terminology here, adding zeros and poles. It's not necessarily that we have a second order system and we're adding them. It's really, I'm using this term as we can study what happens with a true second order system. That's what we were doing the first half of this lecture. And now really what we're looking at is how is behavior of that baseline second order system going to be modified. Although there are times that we will be literally adding poles and zeros to our system, and we'll get to this in Unit 3. So what we're going to be seeing in Unit 3 is that instead of these open loop systems where we just apply a step function and see what the result is, we're going to be able to add feedback into our system where we get to choose what input to put into our system to get some desired output. And effectively what this is going to be doing is a little preview of Unit 3 is when we use the output to influence what the input is, using derivatives or integrals of that is going to be equivalent to adding zeros or poles to our system. So again, more on this in Unit 3, but this is another time that additional poles or zeros can be added to what is a second order system. So how we analyze how our system is going to behave when there's 3 poles or there's 2 poles and a 0. We need our analysis method. So first thing we're going to do is we're going to find the dominant poles of the system. Really, we're going to find all the poles in the system. But what we're going to call, if we have a third order system, the dominant poles are the complex conjugate pair. That is going to tell us that the third order system, let's say it has 3 poles, is going to oscillate. So the dominant poles are that complex conjugate pair. And previously, in a true second order system, those are the only poles that we had. Then we want to identify what our extra pole is. So what's that third pole, or it might be a 0. Now, if it's a third order system, that extra or that third pole must be real because we can only have complex numbers if they come in the complex conjugate pair. And if we have only 1 0 in our system, well, again, it must be real as well. And what we want to do our analysis is that extra pole or extra 0, we want to factor out of our system. So it's perfectly fine mathematically if our denominator has an s cubed term, an s squared, an s, and a constant. But what we want to do is factor it into the real pole in the form of s over negative p plus 1, and then the rest of it, which it's going to again be underdamped, so they're going to be complex conjugate pair. So the rest of the denominator is going to look like an s squared plus s plus a constant term. And then the numerator, again, we want to factor out that 0 in the form of s over negative z plus 1. And we'll see why factoring out this way when we're doing this by hand analytically is going to be useful to us. So really what we're going to be doing is first analyzing what I'll call the baseline system. And what we do is we look at the system when we ignore those extra terms, that s over p term or that s over z term that we previously factored out. So this baseline system is a true second order system. It has no zeros in the numerator and exactly 2 poles in the denominator that are a complex conjugate pair. And the first step of this is do the analysis exactly like we did it the first part of this lecture, because that dealt with true second order systems. Then once we have the baseline, we know what the overshoot is going to be of that system, the peak time, the rise time. Now we're going to estimate the response when we factor in these extra terms here. Now, I will make it clear for this course, what we're doing is really making a qualitative assessment and not a quantitative assessment. So if our max overshoot of the baseline system is like 60%, when we add that extra pole, we're not going to know exactly what value it goes to. All we can say is, well, in general, it's going to be less than 60% overshoot because that extra pole, assuming it's a left half plane pole, because a left half plane pole is going to decrease our overshoot, increase our peak time. And then further we can say, again, qualitatively, oh, is that extra pole close to the real part of the dominant poles? If so, it's going to significantly decrease the overshoot and significantly increase the rise time. So really, if we sketch, we have a good sketch we can draw for our true second order system, and then we'll have a more qualitative sketch, almost a kind of a cartoon that's going to show what happens when we modify it from there to a third order system or a second order system that has a 0 in it. We're doing this all analytically, but we can also do this in MATLAB numerically, and we'll see what the differences are between just our qualitative description and then what MATLAB is going to be able to show us quantitatively.